Disappointed quite a few people who thought we would have now a break, but instead of that, you need to suffer a bit and hear me speaking. So the last two talks today will be a bit of a different take on. So both Ron and I are working on research infrastructure provision, and it will be highlighting how both of us really try to underpin the research of people like you here for the benefit of the society. So, and we heard a lot about big data, and on the bioinformatics side, we're of course of the receiving end of this, and we believe that there's a transitional change going on which is quite dramatic. Takashi knows also a lot about that. He was in research infrastructure provision also for a very, very long time, and I hope it will find your interest what both of us will present today. So let's see how that works. No, that's the wrong way. No, not this way, not that way. This one? No. Nothing. Nothing. Turning around? Okay, so I tried that, but you must have a magic touch, which I don't have. Okay, so just as an introduction, what is EBI, that I direct together with you and Bernie since a couple of months? It's part of the European Molecular Biology Laboratory. It's an international non-profit research institute, and the EBI is Europe's hub for biological data services and research. There are 570 members of staff working there from 57 nations. Around 300 of these are really research infrastructure provisions. The rest is handling some of our other missions. And Takashi, how did you do that? What was the magic? I need to point this way. Ah, that's a good idea. No, it also doesn't work. Takashi, I need your... Why can you do that and I don't? I touch the same button. Okay, okay, let me see whether I can go back. No. Okay, so our funders, EBI is funded by the EMBL member states. So half of the money comes from these guys, from the member states, and the other major funders are the European Commission, the National Institutes of Health, Research Councils UK, the Wellcome Trust, and some other contributions from industry and others. This time it worked. So the mission of EBI as a whole is to provide free. I'm pretty sure I jumped a few slides. Sorry, let me see. I'm really okay. It seems that I have really not the right fingers for this thing. Yeah, maybe.
The charge. Just a little discharge.
Oh, okay. Ah, splendid. Okay, so it was the charger which was nearly gone. Okay, so let's see. Yeah, you see, it works now perfectly. Okay. Finally, let's start again. So the mission of the EBI is to provide freely available data and bioinformatics services to all facets of the scientific community in ways that promote scientific progress. That is our primary mission. Our second mission is to contribute to the advancement of biology through investigator-driven research in bioinformatics. Then we provide advanced bioinformatics training to scientists at all levels, from PhD levels to independent investigators. So as more advanced the level of investigators, as more basic is what we teach. So then, of course, we also try to help disseminate the technologies to industry. And then we participate as part of Elexia in the coordination of biological data provision in Europe. The service mission is central to, and was really the reason why the EBI was set up in the first place. We want to really enable life science research and its translation to medicine, agriculture, bioindustries, and society by providing biological data, information, and knowledge. And what does that mean in practice? It means labs around the world send us their data, we archive it, classify it, analyze, add value, and integrate it, and share it with other data providers. None of our database is really done in isolation. So with Takashi, we worked for many, many years together on EMBL, GenBank, DDBJ. With the Swiss Institute of Bioinformatics, we worked together on the creation of the protein databases even before EBI and SIP came into existence. And then we analyze, add value to the data, integrate it, and provide tools to help researchers to use it. Then, hopefully, this leads to some clever ideas, new hypotheses, new experiments, new data, comes back to us, and we start the cycle again. So it's a collaborative enterprise. And the whole idea is that we move from data to knowledge. Data is just some observations stored. Putting the analysis level on that gives us some information, but really putting these different pieces of information together leads to knowledge that we can use in practicality. When we moved 21 years ago from EMBL Heidelberg to Hingston, we had really only two databases. The EMBL database, which was the collaboration between DDBJ and NCBI and us, and SwissProt, the collaboration between Geneva and us. Since then, a lot has happened. At that time, we were 30 people, 21 years ago. Now we are many more. And there are now a whole raft of activities around genes, genomes, and variation, like ensemble, gene and protein and metabolite expression, protein and protein families, structures, chemical biology, systems biology, reactions, pathways and interactions, literature, and ontology. So it's the whole raft, a whole raft of information which is very widely used by the scientific community. We touched already a bit on big data, and this is a log plot. So this and these are the years, and the different colors are different data types. So the red one here, I should also explain. This line here, if something follows exactly this line, it means it doubles every 18 months. So the red line here is the nucleotide sequence data, which is completely publicly available. So the short read archive, EMBL, GenBank, DDBJ data type of things. And you could see with the coming up of a new next-gen sequencing, there was a huge growth curve for a while. Then we sorted out better compression technologies and such things, and now it's back to the normal duplicate every 18 months or so level. This here, this line here is the controlled access human data. That's just human data. That's all types of nucleotide data. That's just human data. And you can see it has grown very rapidly, and this is also doubling every 18 months. And it's really only the controlled access stuff. Sorry. The green line, you can see that technology is overtaken. This is array data. It's still there's a lot of microarray data produced, but it drops in the duplication rate from this 18 months to now just 24 months or so. So of course these machines, investments were made in microarrays, and people will use it still for a very long time because it's very useful. It gives, for a lot of experimental setups, it can give you the results with an accuracy and reliability of a statistical analysis you want, and you don't throw this away. But at some stage, this will be technology of yesterday, and people will really move on to just deep sequencing instead of using arrays. The blue data here is proteomics data, mass spec data, this light blue one. And the most rapid developing area right now is metabolomics data. But of course, this is magnitudes less than this, yeah, so since it's a log plot. Okay, so this has resulted in already a considerable amount of data we need to handle. So this is our infrastructure setup, a picture from now. So we have around 75 petabytes of disk for storage. And to compute our production, we need something like 40,000 cores. We moved from having everything in one data center at one place to having it staged in a different way. So in Hingston, we have the production database and the so-called staging area. And then we have in Flint Cross, that's just 10 kilometers away or so from EBI, we have an area where we directly write a second copy. So just in case that something happens in Hingston, that we have a complete copy of our production databases there. And that's quite important for those of you who have visited already EBI. Know we have the Imperial War Museum close by. The Duxford Air Show happens every year, and nearly every year one bloody plane crashes sometimes. And maybe at some stage it crashes into our data center. So we are prepared. No. You can come and see it during the day.
You don't have a copy of the people 10 kilometers from only of the data. It crashes during the day.
Oh, yeah, well, yeah, okay. Don't confuse me too much at that time of the day. So that is the production data. We serve all the data out of a data center in Hemel Hempstead. This is run by us, the Hingston one. Flint Cross is a commercial data center, and Hemel Hempstead is also a commercial center run by a company called Jaron. And there we have two identical copies, again, of the data which we deliver to the public. So whenever something is ready for production, it goes into the staging area and is then handed over to Hemel Hempstead, and from there we deliver it to the public. All of these internet connectivity in between are 4 times 10 gigabit per second links, so pretty good. And at the moment, since this internet connectivity is so good, we decided that we will go from 2 instances here and another instance here to having only 1 instance here and having that as the fallback, because now we have triple security, which was necessary when we had not such a good internet connectivity. But with this high-speed links we have now, we can say we can save some money on this and go back to 2 copies for the public instead of 3. So that's the current status, and you see this is sorry. The speed of this is a problem, yeah. But it's not the biggest problem. We know, but if we carry on with this speed, then in 2020 we expect to have between 1 and 4 exabyte of storage needs, and we need something like 230,000 cores to do the production runs. So that is the size of a Facebook, Amazon, Google, and so on data center. And we still have less computational needs than the high energy physics, but we are just 1 dimension below, not anymore like 10 years ago, 3 dimensions below. So we are now bioinformatics becomes a serious player in this field. And where we are very serious, all of the bioinformatics suppliers, is that we serve a much larger crowd of people, while the experiments in high energy physics, the Large Hadron Collider, around 8,000 physicists worldwide use the data. In life sciences, places like SIP and EBI serve really hundreds of thousands every month with life science data, or NCBI in the US or DDBJ in Japan and so on. So it's the amount of user is way, way, way bigger. So if you try to look ahead, what are the challenges and opportunities, then one opportunity is definitely that we get a lot of new data. New next-gen sequencing data will carry on. A lot of that will be driven by variation analysis of humans. Humans are, for whatever reasons, the most popular model organism out there. And we will also see a lot of image data coming soon. So far, we shied away from dealing with image data, but high-resolution light microscopy data, 3D cellular imaging techniques, tomography, and so on, the structural methods, EM and so on, that has changed completely the field, and it will become more commonplace to underpin a lot of the information we provide to our users. So we need to deal with that. Medical data will get more digital and easier accessible, and we can make connections. You heard before already efforts in this field. And there's also the area of unstructured data. How do you want to reproduce experiments if the supplemental data is not properly kept somewhere, if it's at some stage lost? So we need also to work with publishers on this. So this also gives us, of course, a lot of new opportunities to gain new knowledge, to connect to medicine and agriculture, to biodiversity and environmental sciences, to explore the genetic variation data and phenotypic correlates, and towards understanding of human biology. As I said, the humans are still the most popular study object for humans. We like each other more than we think. That's why we study us. So this means we need to focus very well on our users. When we started this, we were delivering our tapes to a few hundred people worldwide. Now we serve hundreds of thousands. So 20 years ago, we knew our users. Now, how do we learn them, their needs? How do we focus on them? How do we do user-driven data integration? How do we train all these people? How do we foster research collaborations that our data collection and the way we design tools will stay in line with the needs of the researchers? And how do we engage with all these new user communities? That are real challenges. And all of that is driven by bioinformatics really going translational. If we look into research versus practicing medicine, then we can see there are some clear distinctions. In research, we usually use English as the language. The legal systems we have to deal with are relatively lightweight. We operate in identical to similar systems. We all propagate open data and open science. The currency of success are publications, and most of the work is grant funded. In practicing medicine, we usually use the national language. We have a very heavy legal framework, very different systems. The data is usually closed. Most of the data is not even published. And there are also sorts of contracts going on to fund these activities. So if we look into clinical data, then nurses or others are collecting data in hospital. It's rarely stored in a computer-friendly, systematic way. The clinicians interpret data and treat patients. There's very little data sharing going on. The data analysis is limited to a few research hospitals. And there are very few tools for data analysis, since data is not available, where you can develop the tools on top. So if we look into the different healthcare systems in different countries, I only used here the UK and Germany as examples, very different models how it is organized. So, but this is really where this translational change, where we can make really a difference. We as scientists and we as bioinformaticians especially. From our point of view, in Europe, what we try to have is that we have institutes for biomedical informatics and with whom we can interact. In bigger nations, there will be more than just one side, but there will be a network with a center of gravity. And EMBL EBI in the framework of Alexia will handle research-style data, sharing between researchers, including researchers. And these biomedical research institutes will have then the responsibility for exploiting the molecular reference data handled by Alexia and EBI, and ensure open research data flows back to enhance the core reference data at EBI and made it available to other researchers. Because there will be so much data in there, in this translational effort. We also need to leverage this investment that drives also research. And that is a big change. How do we leverage that? So our role will be restricted on this reference information. But we have a lot of experience in data sharing. We have a lot of experience in long horizon information management, in integration across biological domains. How do we use large scale disk compute and network? How do we extract knowledge and manage it? algorithms and statistics development, the development of the right methods there, and to work in international and consortium interactions. We have a lot of experience there, and that we want to bring in helping. But this can't happen in isolation, even we're a big place. SIP is also quite a big place, but even we together wouldn't be enough, because there are so many more states. And in Europe, a lot of us came together in Elexia, the European Research Infrastructure for Biological Data, which tries to connect national infrastructures and EBI. There are 12 member states so far, plus EMBL. I may be wrong there, but I'm not, maybe even more, but there are quite a few countries which signed up already, and 5 countries, Belgium, Greece, Italy, Slovenia, and Spain, they are in the process of signing the last documents. So it's growing and growing. And here the idea is that, this is an infrastructure which will support life science research and its translation, like the EBI mission, but that we get all the research infrastructure providers in Europe together. And so, and it has the same background, deals with data, with tools, with computational infrastructure, with standards development, and with training. And the biggest driver, if there would be just one reason why we must have Elexia, then it's the medical data, the translational aspects. Because a lot of this data can't be centralized. It will be illegal. You can't move the data easily from the Netherlands to the UK or from Germany to France. There are different legal frameworks, different ethical standards which needs to be followed, and so we need to find ways that we can interact in a federated system. And the biggest use case is really human reference and study data. So one of the examples is that we started this European Genome Phenome Archive. I showed you this controlled access part. In the US, the equivalent is dbGaP. And it's now run as a collaboration between EBI and CRG in Barcelona. Barcelona is actually not there, and that's Madrid, which is shown there, but it's more to the northeast. Anyway, and this is already a collaboration, but there will be similar sites which need to come up in these different countries, run by some mechanism, this biomedical research institutes or whatever it is, but they need to be federated and work together, that you can really do just very simple things, what we can't do right now. Tell me all studies which are out there on inflammatory bowel disease. At the moment, impossible to find all these sets. If you, let's say we are able to find them, how do I get then the necessary consent by the data access committees that I can download the data sets? If I got this consent, this permission by this DAX, how do I download it? How do I authenticate myself? How do I bring that all into a secure environment? How do I compute on it, get my results, and all the data is securely moved away from my fingertips? That are all questions which we need to work on together. And if we don't do that, we will use the statistical power of combining all of these single observations into big data. You gave the example, and you gave the example of the cancer data. All of the cancer data are rare diseases in some way. So if we really want to have the power of that, we want to have every case together, because then we get statistical numbers which will hopefully help us more. And only if we do it all the analysis in a comparable way, we will have not this Venn diagram of different results. So this is all cries for collaboration. And with that, I say thank you, and happy to answer questions.